Hello again. So this next video will deal with how we mathematically look at the data of a titration. It's going to be probably the most difficult video we'll deal with in this entire class. So bear with me. I will try and help and go as slow as I can, but we'll go through this. So mathematically, when we're looking at pH during a titration, there's generally 4 different regions and 4 different ways we can calculate for. Region 1 is essentially prior to the titration. It is always the easiest region, where essentially 0 mils of the titrant has been added. 0 mils of base, 0 mils of acid. You treat say if you're adding base to an acid, you're treating your acid like a strong acid or just a weak acid. Region 2, during the titration but prior to the equivalence point. You have to set up an ice table, you have to cancel out certain things. But in a strong acid, it's still pretty easy. In a strong base, it's still pretty easy. In a weak acid, we have to set up a buffer. At equivalence point, in a strong acid, strong base is very easy. Weak acid, weak base, that's a little bit more challenging, and we'll deal with that. And finally, after equivalence point, where any point after equivalence point when we've added base or added acid, what happens to the pH and how does it jump. Now, an ice table will greatly assist us with calculations. We can also use Excel or various things to help us. Now, when we're calculating a strong acid, strong base, don't forget this is a common occurrence. We'll always need pH is equal to negative log of our HA. pH is equal to negative log of HA. This is always going to be there, except for when we go basic. But during the titration, we have to follow these steps. We're going to turn molarity and volume. We're going to turn molarity and volume to moles. We're going to then subtract out the limiting reactant. Then we're going to turn moles back into the new volume. We'll say M prime. And that's because we not only neutralized, but we also diluted. And then we can calculate pH equals negative log of H plus. At equivalence point, at point 3, when moles minus the limiting reactant, moles of acid minus the limiting reactant equals 0. And you try to take the negative log of 0 and you get a undefined error. That is because it is perfectly neutralized strong acid. And so in this case, this equivalence point, pH equals 7. If you recognize that the acid and base have perfectly neutralized each other, pH is 7. But on point 4, we do the same thing. We do MV to moles. We minus the limiting reactant. See, we turn the moles back into molarity. But now, since it's more base than acid, we have to then if we find the negative log, this gives us POH. And then we have to convert that into pH. So we have to be mindful of every step in the process of what we're doing and what reactions are being viewed. So, now, with that in mind, okay, we'll practice. You can write out, if you're smart, you don't have to be smart to do this, but you can write out an equation that helps us understand this. I'm going to use Excel, and so pH is negative log of HA. 0.2, molarity times volume in moles. We subtract the limiting reactant, we turn moles back into molarity. pH equals negative log of H plus. 3 is 0. And then 4, we're just repeating that again. You can write an equation that works out your ice table. As long as, let's leave volume in milliliters, you can write out a generic equation that, follow me here, that molarity of acid times volume of acid minus molarity of base times volume of base, all divided by volume of acid plus volume of base. If this gives you a, if answer is greater than 0, this is acid molarity at point C. If the number is equal to 0, we're at neutral. This is pH 7. If the number is less than 0, so if the number is negative, then this is a base. The base. And so we have M prime is going to be the absolute value of that negative. So make it positive. That's M prime. That's a base. And that's going to be pH less than 7. This guy's going to have a pH of greater than 7. But if you know how to set this up, you can easily solve at any one point. You still have to take the negative log of your thing. Still have to take the negative log of your thing, but with that in mind, we can solve this. So let's try this with Excel, but real quick. We have a 25 ml solution of HCl is titrated with 0.3 molar of NaOH. It takes 13 mils to reach equivalence point. So first, what is the concentration of acid? Then what is the pH at these various points? So let's type this in. So we have MaVa, MbVb, we have 0, we have 5, we have 13, we have 15. Okay. Okay, with that in mind, let's look at this. I'm going to use Excel. I've typed this in. Okay, let's go drag that a little bit over. There we go. Now, step 1 is finding our concentration. Our concentration, Ma, is going to be equal to Mb times Vb divided by VA. Just as a quick reminder. So I can set that equals MB times its equivalence point is at 13 divided by VA. So this is my concentration. Now our equation that I showed you is that MA times VA minus MB times VB, put that in parentheses, and that is equal to, and divided by VA plus VB. Okay. Now, using this at every single point, drag that down so it's out of the way. So let's look at M prime. Gonna copy that and place that as a number. Just the value. Okay. So I can write an equation. Let's go to grab these and copy those down. We don't need to make it harder than it needs to be. So what is the molarity at each of those things? So let's set that up. Equals, in parentheses, MA times VA minus MB times VB, all divided by VA plus VB. Concentration, surprisingly, has not changed because I've added no base. Now if I add these values and I scroll down, the titration after 5 mils, 0.156 molar has been partially neutralized to 0.08. To this point, all of it's been neutralized, and so it's at 0. And at this point, a little bit over all of it's been neutralized, so it's now in the base region. So our pH is going to be just negative log of the log base 10 of our concentration. So this guy, solving that. pH is 0.806. Scrolling down, pH has jumped from 0.8 to 109. Not a huge jump. If I try to solve this one, I'm going to get angry sign. It's angry because it cannot calculate pH of 0. The pH of negative log of 0. So it's just pH 7. That's the one thing you have to remember. You can't just solve that. This one, we want positive 0.015. Now remember, this is a base now, so now it's no longer negative log, it's 14 plus log base 10 of this value, because this is an OH minus. So it's jumped from 7 to 12.176, or 12.18. So with that in mind, you see right there, we've solved this relatively easily and relatively quickly. Now you can spend all your time plugging these into your calculator and setting that up, but if you know how to do it, it is not as hard as it need be. Okay, with that in mind. So I did that, 0.81, I found what is it, found the concentration, found the pH, 0.08 is a pH of 1.1, 0, you get pH 7, and then 12.18. What about working with a strong base? So now we suddenly have 15 mils of base, 0.75 molar acid, 10 mils of acid perfectly neutralizes, and I want 0, 5, 10, 15. Okay. Once again, we can set up the ice table. We can do all that, but we can really just, if we have Excel and we know how to use Excel, we can go ahead and get that done. I'll just delete all these. Yeah, it's going to be all grumpy because now I'm deleted all my things. Now it's just the other way around. MB, VB, MA, VA. And this is going to be MB, VB, MA, VA. That just changes how we look at this. But we don't know the concentration, but we do know the concentration of acid is 0.75. We know we use 15 mils of base. 0, 5, 10, 15. And so 0.75 times 10 divided by 15 gives us a concentration of base of 0.5. This is going to, of course, equal this in parentheses times this minus this times that. And the beauty of this is and then I got to dilute it. Got to dilute it again, so we have the in parentheses VB plus VA. So we have, the beauty of this is I can work with, oh shoot, I didn't drag these down. No, I can't paste that as numbers. The beauty of this is that as long as I know, I go, this is base, we can work this out. That base, neutral, acid. Base, neutral, acid. So we have to kind of work in reverse. So we're going to say not, this is, we'll just say POH. 0.125. Just we'll say negative log 10. So pH becomes 14 minus the POH. 14 minus. So if I drag that down, so it starts at 13.69 or 13.7. After we neutralize a small amount of this, it goes to 13.27. At the equivalence point, it drops to pH 7. And then after 5 mils past the equivalence point, it is dropped to 0.903. So it is dropped a huge amount by 5 mils afterwards. So it becomes rather simple situation at this point. I could ask you for any volume. Let's go ahead and add another one. I'll add a ridiculous one. So 0.5, 15, 0.75, and I'm going to say at 9.5. I've just about at equivalence point. At 9.5, what is the pH? I'm almost there. And so I drag that down, figure that out. So within a half of mil of the equivalence point, it is only within 12.18 pH. So it has not changed drastically at all. Not drastically at all. I can do one more. one better. We'll say 9.75. Down. 9.75. Drag these down. It is dropped to 11.88. Still not within a quarter of a mil of at the equivalence point, and it's still very basic. So that's what it means to be a strong acid, strong base. It doesn't change by a lot until we get right on the equivalence point. So with that in mind, let's go ahead and keep going. So now a weak acid base is by far a much larger pain in the ass, because we can still do all the same points, but none of them are direct gimmies, because at point 1, where it's all acid and all base, you have HA breaking down into H plus and A minus. And so you set up your ice table, you get a Ka expression that Ka equals x squared over HA. So it essentially becomes negative log of the square root of Ka times HA would give you your pH. So to find your H plus, you have to take the negative log. Now, prior to equilibrium, we have, say, HA, and we're adding OH minus, which is then going to partially neutralize this down to A minus and water. And then we have a secondary reaction where HA and water is then going to partially form some hydronium and A plus and A minus, sorry. And this is reversible, and so we have a buffer situation. So we have to have MV to moles. Then we're gonna subtract our limiting reactant. And now here's the beauty, though, because at this point the moles of A minus and the moles of HA are going to be the same. You don't actually have to calculate your molarity, but we'll go ahead and do it. We'll do it back just so we don't confuse ourselves later. Molarity, and then we can use the Henderson-Hasselbalch. That we have essentially the pH equals the pKa plus log of A minus over HA. Then at the equivalence point, we have a totally different expression. Now that HA and OH minus has gone completely to A minus in water, you have a secondary reaction where A minus and water is going to reversibly reform some HA and OH minus. That you have a situation where KB is equal to x squared over A minus, and the negative log of the square root of KB times A minus is going to give you the POH, and you can turn that into pH. But you have the added pain in the butt that you have to calculate for the dilution of A minus. So A minus is now, we essentially turn moles, molarity to moles, and then moles back into the new concentration. And so that you have to take that into account. And of course, in point 4, it's just all OH minus at that point. You still have to go MV to moles, subtract the limiting reactant, and then moles back to molarity. You still have to do that. But the idea is that at that point, the pKa can be safely ignored. The pKa can be safely ignored. So with that in mind, so we have situation 1, just weak acid. And so it follows a normal weak acid. Situation 2, first we neutralize some of the acid, and then we have a buffer. Situation 3, we neutralize all of the weak acid, and now we have a weak base. And have to deal with that. And then situation 4, we just have a strong base. So we have to deal with that. Weak acid, buffer, weak base, strong base. And so we have to write our own situations. Now, we can still use that same equation. We can still use that same equation and help us solve this. We can still say that MaVa minus MbVb over Va plus Vb, and that's going to give us the molarity. When it's in situation 1, when essentially you'll have to recognize when Vb is, I guess when the number is equal to Ma, it's just going to be the negative log of the square root of Ka M. When it's situation 2, when this number is greater than 0 but less than Ma, then we have pH equals the pKa, which is going to be equal to plus log of our number over our limiting reactant. That's our A minus, that's our HA. When our number is essentially 0, we can no longer just ignore it. Now we have to say that this is a base. It's base now, and it becomes, we have to say negative log of our 10 to the negative 14th over our Ka times MaVa over Va plus Vb. We have to take that into account. And then situation 4, when this number is essentially less than 0, it's just the usual, it's a base, and we just have to do the negative log of the number and then turn that into an acid. So we can still use a lot of the same setup for our neutralization, but now we, at least to figure out what situations we're in, but now we have to do a lot more calculation depending on the situation we're in. So it becomes a little bit trickier. So let's look at our PowerPoint. What's this situation? What's this problem? This problem is a 25 ml of 0.156 molar acetic acid is titrated with 0.3 mils of NaOH. And so basically the first problem again. The first problem again, except now it is a weak scenario. So let's look at this. 0.3, 0, 5, 13, and then 13 and 15. So with that in mind, I'm setting that up real quick. Okay. Now that I have that set up on Excel, we don't have to do this, but now we have to take into account our other things. So I'll just say the H plus. H plus, if situation one, H plus is going to equal square root. It's going to be square root of Ka times Ha. Situation 2, it's going to be equal to, it's going to be negative, well, it's going to be essentially, we can just say Ka times M prime over the limiting reactant, which would be Mb times Vb. Actually, we have to take into account so Mb times Vb over Va plus Vb. Such a pain. Such a pain. And situation 3, it's going to be Kb, square root of Kb times Ma times Va over Va plus Vb. And situation 4, it's going to be just OH minus is going to be equal to essentially M prime. So our Ka, let's make a little space. Insert here our Ka. Our Ka is not going to change. 1.8 E negative 5. In this case, our situation has not changed, so we just say equals the square root of this times this. On situation 2, it's going to be equals this times this, and then here's the hard part. We got to figure out how much base we have. So this, so we have to divide this by, in parentheses, we'll say this times this divided by this plus this. Got to make sure your parentheses are all right, or else you're going to go right off the deep end. Okay, there we go. So it's really, really small. Situation 3. So what's our Kb? Our Kb is going to be equal to 10 1e to the negative 14. And we're going to divide that by our Ka. So there's going to be this equals the square root of our Kb times Ma times Va divided by, in parentheses, the sum of our volumes. So it's changed again. Acid, base. And now this is just going to be equal to -1. Let's just say times that. Acid, base. Okay, with that in mind, at this point, now that we've figured out all of our stupid little scenarios, we can just say the negative log of these. Negative log base 10 of this pH of 2.775. pH of that is 4.54. Since this is a POH, so we have to take equals 14 minus that, 8.87. And at the second one, 12.17. So we have our 4 values. Now, yes, maybe I could have set this up on a calculator a lot easier. Maybe you have to use a bunch of paper to do this. There's a lot of different ways to go about doing this. But when you're using a lot of the same equations, you can set some of these guys up. But it's tricky. It's a tricky trap. So make sure you know what is your total volume. Make sure you know all these things and all the steps so that you don't get tripped up here or there, what have you. But with that in mind, I don't usually ask a ton of questions about this because this is really challenging as heck. But 2.78, 4.54, 8.88, and 12.18. That's what I got. And so it shows you can absolutely do this with Excel without too much difficulty, but setting this up otherwise can be a pain. And the last slide I'll leave you with today is something back to a little bit easier. I promised I'd look at this. Polyprotic acids. That's the final type of strange acid-base scenario we'll look at. Polyprotic acids are acids that contain 2 protons. It is lost systematically. So sulfuric acid, carbonic acid, phosphoric acid are some of the big ones. But as long as they are not strong acids, they experience multiple equivalence points. Well, I mean, they have multiple equivalence points with multiple Kas. However, if it's a strong acid, you cannot find the first Ka. But the idea is, until the first proton is completely lost, you're not going to start touching the second proton. And so we see a huge jump as we completely remove the first proton, and we start to remove the second proton. Now, in practice, the second equivalence point should be about twice the volume of the first. So if it took 25 mils to neutralize the first guy, it should take 50 mils to neutralize the second guy, because you've already used up 25 mils of acid, or 25 mils of base. Now, we can potentially get a half equivalence point somewhere between 25 and 50. About halfway between that would be, 37.5. And so the pH at that value would be the Ka for that second loss. But remember, with a strong acid or strong base, you cannot get the Kas, so do not try. Do not try. But that is where I will leave you for today.